Assalamu alaikum guys. Good morning.
Assalamu alaikum, miss.
Alaikum salam.
Assalamualaikum.
Alaikum
How are you, miss?
Alhamdulillah, I'm doing fine. And I hope all of you are doing as well good.
Yes.
Okay.
Ya Ramadan Kareem, miss.
Ramadan Kareem. Inshallah, tomorrow onwards we'll be fine. Fasting, right?
Yes.
And may Allah bless us in this Ramadan. Because we're going through a very tough time, right, guys?
Inshallah, miss.
Inshallah.
Inshallah.
Now, guys, yesterday I was doing Electromagnetism chapter. So I have decided that let me complete this full chapter. Then I will go back to paper 4, the remaining question of current electricity and the electromagnetism questions I'll be doing with you together, right? Because with the flow I want to go, because if you once I start, I don't want to interrupt it another. Because this is a chapter you need to understand very carefully. So I will go all through the chapter initially, means I'll be completing the whole chapter. Then I'll go for the past paper one more time. There, whatever question we left behind from current electricity, I'll be doing with you at that moment. Okay, guys? So,
okay.
Fine. So now, I want all of you to open your record book, as well as I'm going to share the screen with you. There, I want to start that chapter one more time. Okay, let's see. Yes, I hope you can see the, yes, you can see that sharing of this screen. So yesterday, I have finished this topic regarding to understand. Yes, let me admit the other students who are trying to join. Everyone, yes, we join. Now, let's go for that topic again. So, yesterday I was checking this one about when you are having the electricity out of the page or into the page, then what will be the possible pattern of the magnetic field lines that will be created around the current carrying conductor or a single wire. Okay, that was our case we were doing it. Now I want to check again what are the properties of the magnetic field that is created by this particular pattern. So as I said yesterday, you have noticed that this pattern of the magnetic field lines are kind of a circular one, and concentric we say means the point where the some of the students is joining. Let me allow them. Okay. So we were discussing that these magnetic field lines will be concentric, and they were supposed to be from a single center, and that will be the point where the electric wire has gone through. Okay, and from there, these circular magnetic field lines will be created. That will be the center, and then, as I told you before also, that they are going to have an increasing difference between the lines. Means the diameter will keep on increasing. The difference between the lines will keep on increasing as you move away from the point where the wire is going inside, or the point of the or you can say as you're moving away from the center. So let us just check all the properties that can be seen in this particular pattern of the magnetic field lines. I will read out and explain to you. First of all, I wrote the magnetic field lines are continuous concentric circles around the wire. Okay, continuous you can understand, because once it will start, it has to complete the circle. And as I said, concentric circles around the wire. So it means that the position of the wire will be acting at the center, and around it, all the circular lines will be created. Point number 2, the strength of the magnetic field line is strongest close to the wire. Means the first line or the second line which is coming, which is close to the wire, will be the part where the magnetic field strength will be strong. Now, why will it be strong there? Because as I told you, that initially the wires, around the wire, the magnetic field lines will be closer to each other. The more you go away from the center, they will be moving away from each other, because the diameter or the difference between the two magnetic field lines will keep on increasing. So before also in magnetism we learned one more thing, that when the magnetic field lines are closer, that part of the field will have a strong magnetic field, or the magnetism will be strongest there. So that point we brought it over here again, that the strength of the magnetic field is strongest close to the wire. Okay, now number 3, the strength of the field increases as the number of wires and the current is increased. Means, here I have given you the example of a single wire passing through the paper or the curve, as I told you. But if I make there 3-4 wires going through, means I'm going to make a loop and 3-4 wires, I'll make a loop of a wire and all those wires should go through it. Then I will see that the strength of this particular magnetic field will increase. One more thing I can do, that is I can increase the current passing through it. How will I do that? I can use a battery which is having more EMF, or I can use a collection of cells which can give me more EMF. That will be of course in a series circuit we learned before. Then we'll see that this magnetic field that is created by this wire will have a strong magnetism. Okay, now check the next part. We said direction of the field can be either clockwise or anti-clockwise depending on the direction of the current. Already, if you remember the two diagram that we had initially yesterday we discussed, there we say when it is going into the page, that can be found it is, if you just look at the diagram, I'll just go up and check the diagram there. Okay, just 1 minute first, let me see. It might be someone waiting there. No, everybody joined. Okay. Now let me check that diagram one more time. That is, we said when the wire is going into the page, means the current passing through the wire is having a direction into the page, then it will become clockwise. And when it is out of the page, it will become anti-clockwise. So like that, we'll not remember. We have a method. I'm going to explain to you that method right now. Now look at this. We say there, yes, we say direction of the field can be either clockwise or anti-clockwise depending on the direction of the current. As I said, if the direction is into the page, then it will become clockwise. If it is out of the page, then it will become anti-clockwise. Okay. Now, point number 5, direction of the field at a point is the direction of the force on the end pole of a magnet at that point. Now, if you remember, whenever we discuss about this thing, that what will be the direction of the magnetic field, in case of static electricity, I told you that we are going to always consider a positive charge. And in case of magnetism, we'll be always considering about a north pole. So here we are saying, if I place a north pole of a magnet in that particular point, whatever force that north pole is going to experience, that will be the direction of this particular field created by the wire that is carrying a current. I hope you understand, girls. You have to place the north pole of any other magnet. Of course, it has to be a permanent magnet. And we're going to bring it and place that north pole at that particular point and check what is the force experienced by this north pole. That will be the direction of the magnetic field. Okay. Now, as I already mentioned, that how we are actually finding out the clockwise and anti-clockwise thing, I say that we are going to apply a law. We call it right hand grip rule. That one I'm discussing with you now. Rule for field direction. Okay, guys, let me remind you. In this particular chapter of electromagnetism, we are going to use both the hands in many cases. Sometimes it will be right hand grip rule, sometimes same is left hand rule, right hand rule. So that two hands are very important for us, because the fingers we are going to represent a few quantities that will give us the result of the interaction between the magnetic fields and all. Right now we are discussing about right hand grip rule. Means all of you are going to just have your pen in front of you. So grip the pen like this and check how our hand turns out to be. So if I just move down, you'll see I have given you the diagram as well. See, I gave you the diagram. Means you are having a wire which is passing electricity through it and you are going to grip it. When you are going to grip it, that time, if you just look at my diagram, I say, when you are going to grip a wire, right now you can just grip your pen and check it. That time you see your thumb is going upwards. So if the thumb is going upwards, that time we'll say, if I match the thumb with my direction of the current, then the curved fingers is going to give me the curved fingers is going to give me the direction of the magnetic field that is produced there. So right now, the way I have given you the diagram, which direction of this current is there? Someone who can tell me, is it into the page or out of the page, girls? Someone please tell me, what is the direction of the current there?
Out of the page.
Out of the page. So in out of the page, we learned that it has to be anti-clockwise. Now, sorry, it will be clockwise. Out of the page, it has to be clockwise. No. It's anti-clockwise, definitely anti-clockwise. So just look at this diagram. Didn't I give an arrow which is giving us the direction of the magnetic field? Because our curved fingers will give us the direction. If you just look at my diagram, you'll understand. Here we are showing the diagram like this, means our curved finger is going to give us the direction of the magnetic field lines that is produced. We said it will be the concentric, circular, continuous line. And the thumb will always give us the direction of the current. Now just make it thumbs down, girls. Then check what is coming up. When you make it thumbs down, then the direction of the current is becoming into the page. Isn't it, girls? Then look at your curved fingers. Where are they pointing you? They're pointing you to the clockwise direction. I hope, girls, you have the difference between, you can understand the difference between clockwise and anti-clockwise.
Yes.
Okay, fine. And do you remember in general physics, in moment chapter also we had these two, clockwise, anti-clockwise. Do you remember that? That was clockwise moment, anti-clockwise moment. We had the discussion ACN equals to CN. Remember about that was the condition of equilibrium. Okay, now let me see. Okay, one of the students is waiting. Let me check. Okay, now I hope you don't have any doubt about it. Did you match with your right hand about the into the page? Did you match it with that, guys? Did it match with you? Guys, I want to hear from you. Did you match your right hand by placing it into the page?
Yes.
Fine. Yeah. It means that you have understood, because we are going to refer to it many times. Whenever we'll say according to the right hand grip rule. Even in the question paper, they'll ask you to write down what you mean by this right hand grip rule. So you need to remember that thumb is going to point, if we grip the wire with our right hand, then thumb is going to show the direction of the current, and the curved fingers is going to show the direction of the magnetic field produced by this particular wire. Okay, fine. Now let's go to the next topic, that is magnetic field around a solenoid. Okay, now let me tell you, here we are going to discuss it in different situation. But if you remember, in magnetism, we had this topic, solenoid. Do you remember what was that thing? What is a solenoid actually? In fact, in this topic also I wrote it. Okay, let me continue. A current produces a stronger magnetic field if the wire it flows through is wound into a coil. Means we'll take a support and think about, you have a cylindrical shape, means a paper or just a rod, wooden rod you have. Okay, so on the top of it, if you just keep on wounding a wire, it will turn into a coil. And then the both ends, if you just look at my diagram, we wound it on a support. That is, if you just look at the box-like thing that I drew in the middle, it is actually not a magnet here. It is just a support. So on that top of that support, I just wound the wire, and the two open ends came out and joined in a circuit, means in a source of electricity. So after that we are saying, and then I wrote it N and S outside. Did you notice? And then I give some circular lines. Do you remember where we had this type of lines before? How does it, this pattern looks like to you? Does it resemble to anything that we learned before, girls?
Magnetism.
Definitely, it is magnet. The pattern or the magnetic field that is produced around this coil is actually nothing but the magnetic field pattern around a permanent bar magnet. Okay, so what I wrote, check. A solenoid is a long cylindrical coil made up of number of turns of wire. Okay, it's up to you how many turns you want to give, because if you give more turns, the strength of the magnet that is produced there will be increasing. When current passes through a solenoid, a magnetic field is produced around it, which is similar to that of a bar magnet. But let me remind you one more time that that rectangular shaped thing that I drew in the middle, actually it is not a magnet. It is a support. On the top of it, I have given the windings of the wire. Okay, this is not a magnet. So I'm saying, or we are discussing that when you make, okay, first of all, what was that thing? It was a long wire. I took a copper wire, which is an electrical conducting wire, and then made the shape of a coil, and we pass the electricity through it. So we are saying that if you do it like this, then this particular coil that you have already made and passed electricity through it will act like a bar magnet. That is why we drew the magnetic field lines around it just like a bar magnet. But how will you understand which side will be the North Pole and which side will be the South Pole? For that also we have a method. So we come to the other part. Let me read out for you. Okay, which is similar to that of a bar magnet. Okay. North Pole forms at one end and South Pole on the other end, depending on the direction of the current. The polarity can be found by the right hand grip rule. See, again the right hand grip rule came here. But I'll explain to you. Before that, let me just explain one more time that particular point. That is, here we have a solenoid. A solenoid is nothing but a long cylindrical coil made up of a number of turns of wire. And then the open end is going to be connected to a cell or a battery, depending how much electricity you want to pass through it. And then after a few seconds, if you pass electricity through it, this particular coil will start acting like a normal bar magnet. Okay, normal bar magnet. Okay, let me see if there's someone is giving me a message. No. Is there a message? No. Okay, let me get it. So it is acting like a bar magnet, as I said. And then after this, when we are going to find out the direction that is produced, means which side will be the North Pole, which side will be the South Pole. For that, we have a formula that what we again say, it's called right hand grip rule. Okay, now guys, before the thing that I discussed with you, their right hand grip rule, in the right hand grip rule, thumb was giving us the direction of the current. Do you remember? And the curved fingers were giving us the direction of the magnetic field lines. Now, if we just look at the two small diagrams that I gave you right now, first diagram, if you just look at it, the way I placed my right hand grip, just according to the diagram, if you have the laptop or mobile, you have the screen sharing thing right now with me. So match your right hand, making a grip and check with it. So what I said, if you look at it, in this diagram, the positive side is connected. And did you notice the curved fingers? I gave the arrow with all the coils that is going upwards, isn't it, girls? So in this situation, the curved fingers will give us the direction of the conventional current. This is so important, guys. Yesterday also, I told you that in this whole chapter, we are going to discuss about the conventional current. That is, it has to be from the positive to the negative. So if you look at my diagram, from the positive, it is going for, all the arrows are going for upwards. Means if you keep your hand, the curved fingers are going upwards. So you'll be getting the thumb on the other side. So we are saying wherever the thumb will be there, that side will be the North Pole. So match with my diagram, then it will be very clear for you. The North Pole is created, the place where we are, the arrow is showing, sorry, our thumb is giving us the direction. If you just look at the other side of the diagram, the second diagram, just match with your right hand one more time, the grip, then you will see that the negative side of the cell or the battery is connected. And the curved fingers all coming downwards. Then I give the arrow all downwards. Then this thumb is also giving us the North Pole. I hope it's clear for you now, guys. It entirely depends on the direction of the current or direction of the conventional current, and always the thumb. If you match with the direction of the current, your thumb will be always pointing to the North Pole. So now it is clear for us how to get the North Pole or South Pole in a coil where it is acting like a bar magnet. So girls, tell me, do you have any doubt regarding this topic that I discussed with you? Anyone?
Yes, about the characteristics, the points about the
Yes.
directions.
Okay, which one there?
There is, wait, let me see.
Yes, yes, I'm telling you.
About the properties of magnetic field
Uh-huh.
in number
Could you
number
read out?
5.
Could you read out again? I'll explain.
Direction of the field at a point is the direction of the force of on the end pole of the magnet at that point.
Okay, fine.
Why is it not south pole? I mean,
okay, I told you, right, that in case of electricity, we always choose the positive charge. We never discuss about the negative charge. And in case of magnetism, we will always choose north pole, not south pole. It is something decided by the scientists. We are going to do all the time. We'll be placing north pole, no matter whatever the magnetism or whatever the direction of the magnetic field, direction of the current, we'll be always placing a north pole. A lone north pole, we say, but as it is not possible, you know that. So we are saying that a north pole of a magnet we are going to place. Okay. Now, I hope the rest of you don't have any doubt, right, girls? Okay. Now, let's see this. Okay, as I already told you that this coil is acting like a normal bar magnet. So we can expect that all the properties of a normal bar magnet is going with the same one. So let me just read out. You'll find it similar, in fact, very similar. Point number 1, the magnetic field lines are close and continuous curves. Did you understand what point I wrote here? Continuous curves. If you just look at the pattern, isn't it a curve? It's not a straight line. When it is coming out from the north pole like a bunch and goes as a curve and ends at the south pole. So I'm saying that one as well. The field lines are directed from north pole to south pole outside the solenoid. Outside the solenoid. Because what is a solenoid? As we say, these are nothing but a cylinder. On the top of the cylinder, we're going to bond the wire. So outside the cylinder. The field is strongest inside the solenoid and is weak on the outside. Now, you might be thinking why it is strongest inside the solenoid. Because, you know, all this line has to complete inside. On the outside, it is from north to south. Inside, it is going from south to north. So inside, all those magnetic field lines are kind of bunched together. So definitely, the more the number of magnetic field lines in a certain area, the more the magnetic field strength. So we are saying inside the solenoid, it will be the strongest. And when they go outside, it will just spread out all over. Okay? Now, let me check. The next point, what do we have here? The field strength increases by the increase of number of turns of the wire. I already told you that if you make more turns, you will get a stronger magnetic field. Okay. Direction of field is found by the right hand grip rule and depends on the direction of the current. Okay. This one already we discussed. So in this particular case, when you want to find out the direction of the magnetic field that is created there, or what will be which side will be north pole, means actually that is nothing but the direction of the magnetic field. That one we have to discuss by the right hand grip rule. Okay, girls, do you have any doubt regarding this topic? Let me just check. Again, I can share. Is there any message? Let me see. There is some message for me. Let me see. Okay, I will do. Yes, dear. Yes, Habiba, you are asking me this one now. You have to write down all the notes. Definitely. Because you need all these notes later. Of course, you'll be writing the IGCSE. Then you need to have all of it. Okay, guys. Now, after that, I want to just go to the next topic that I have in this particular chapter. That is how to make an electromagnet. Okay. If you remember, when we were studying the magnetism, we discussed about this a little bit, not that much. We said that this is kind of a magnetism which you can start, you can switch on, you can switch off, whatever you feel like, you can do that. We discussed like this. Okay. Now, and permanent magnetism is the one which is going to be for a long time. Once it is created, it stays for a long time, and you cannot control it. You cannot, and it's kind of a long procedure. But electromagnet is like that. That you can.
Miss?
Yes, dear.
Miss, did you stop screen sharing?
Yes. I'll be giving after a few seconds because some students are waiting. I can't see them. That's okay. I'm checking. Okay. Yes. So if you just look at the pattern, first you check one thing. I said that we are going to make an electromagnet of it. This time the rectangular block that I drew in the middle of the solenoid is actually the core. This is not the support. As I told you in the previous topic that we were having a support on the top. I have the windings of the wire. Now it is not that. Here we place the core. What is a core? A core is the one I want to make an electromagnet of, because it will be turning into an electromagnet. Okay, let me see this. Girls, I don't know, some of you are joining very late. Why? You know the timing. Okay, let me just inform you one thing, girls. You know that tomorrow onwards, inshallah, we'll be having Ramadan. So it is decided, and you'll get the notice also today, that during the Ramadan time, we'll be having class starting at 10 a.m. 10 a.m. to 12, 10 to 11, 11 to 12, then half an hour for salah break, then 12:30 to 1:30, 1:30 to 2:30. Four classes we'll be having. Today you'll get the timing one more time from the school, but I'm just informing you that this is how we are going to have the class. Okay. Yes, dear, because we need to complete the syllabus. And let me inform you one more thing, guys. As we, okay, do you remember since when we are having this online classes? Do you remember? Yes.
March.
Yes.
14th of March or maybe 15th.
Yes, yes. It means that we are already more than a month we have had these classes, right? So you remember at the end of my syllabus and everything, all of the subjects are going to have some evaluation, online class evaluation we call it. So please do study the way I'm doing the past paper and everything, just like you're studying in the school, because we are going to have an evaluation. And what type of evaluation will inform you. But by the time you continue with me, the way I'm doing the topics, because we'll consider that as I told you, you're in grade 9 and you'll be going to grade 10 within 2 months, then you'll be having your IGCSE. So we cannot give any reluctant behavior here. We have to be very serious, and as I said, we'll be having an evaluation for whatever we are doing online classes. And mostly, you know that the almost the full second term we has gone for this, right? Okay. Now let me see. I'll go back to the electromagnet topic. If you just look at the circuit, I have a solenoid, and inside the solenoid we place a core, and then that is connected to a switch and a cell or a battery. Here I have used two cells. This is just a battery we have. So I said it consists of a solenoid wound around a core which is made up of soft iron or mu metal. Now let me remind you, soft iron everybody knows. And what is a mu metal? It is kind of a, you can say an alloy, which is a good magnetic material. Okay. And when you pass electricity through it, okay, first of all, girls, tell me one thing. What type of electric source I'm using here? Someone give me the answer. What type of electric source we are using here?
Battery.
But it has another name. I want to know that.
Cell. No.
Current.
Yes, who said?
DC.
DC. Very good answer. Who said that, dear? I can't see you because I'm on the screen sharing now. Who's that?
Anode.
Very good.
Anode.
Yes, dear. It is a DC. Because we'll say, do you remember we learned when you want to magnetize something, you have to use a DC. And when you are demagnetizing a magnet, you have to use an AC. So here also you have to remember that one. You cannot just draw an AC and say, okay, we are using electromagnet here. Okay, here we are showing now. So come back to this one. We have a switch. Now, as we said, when you pass the electricity through it, within a few seconds, it will turn into a magnet. Okay, fine. Now, what is this advantage that we have for an electromagnet over a permanent magnet? Means when we have a permanent magnet, why do we need to have an electromagnet? Because we learn later in some of the appliances, we need to use a magnet which should have the property that whenever we need, we can make it a magnet, and after that we have to demagnetize it immediately. And the process has to be very fast. So in those cases, we need to have this type of magnetism. Okay. Now I want to just go back a bit, okay, because we have less time. Okay, let me see. Someone give me a message. What is the doubt here? Okay, because between magnetic and electromagnetic. Okay, fine. Yes, for the magnetic field, electromagnetic field, no difference. Because what is an electromagnet? When electricity passes through it, there is a magnetism created around it, and that creates a field. So you saw that whenever there's a single wire, we are getting a magnetic field which is having a circular magnetic field lines. But when we are using a solenoid, we are getting a magnetic field that is just similar to a bar magnet. So there's no difference. Magnetic field produced by an electromagnet will be known as electromagnetic field. But that is very much similar to the magnetic field that we learned before in our magnetism chapter. So basically, no difference about it. Okay, now, let me go through that advantages of an electromagnet over a permanent magnet. That is, Their magnetism can be switched on and off with the current, unlike permanent magnetism or permanent magnets. I told you before that whenever I want, I can make it a magnet and switch off the electricity, it loses magnetism. So this is the first benefit or first advantage we have. Point number two, they are temporary. Definitely, the moment I will switch on, it will be magnet, switch off, it will be gone. So it's a temporary one. Their strength can be varied easily by varying the current passing through them. Means if you have a permanent magnet, you cannot change the strength of the magnet. But here, if I increase the voltage, the magnetism is strong. If I decrease the voltage, magnetism will be weak. So this option also we have. The next point is that the position of the two poles can be reversed by reversing the direction of the current. Means few minutes earlier, I showed you that one, that with the right hand grip rule, if I apply it with the direction of the current, then thumb is always going to give you the north pole. So if I just change the direction of the current, then that north pole will become south pole. So anytime I want, I can change the poles of the magnet, the one we call polarity of the particular magnet, whenever we want, just by changing the direction of the current. That's it. Okay. So these all, let me remind you, these all will help you to solve paper 2 questions. Okay. Now we need to go for application that comes in paper 4 as well as in paper 2. Means where do we actually use all this magnetism or all these electromagnets? Since we are saying that we have some advantages of it, so we need to have some uses of it as well. We wrote first of all, see, magnetic relay. Now let me remind you, here we are learning relay, but the basic application of this magnetic relay will be learning in grade 10 electronics chapter. There we say the most uses of magnetic relay will be discussed in that chapter. But right now we know what is a magnetic relay, how does it work, and why do we need to have it. Okay. It is used to turn on and off a powerful high current circuit with a low current circuit. This definition you'll remember because this definition comes in terms of the paper 2 question. What did I say? It is used to turn on. Okay, turn on means switching on and switching off. We can switch on and switch off a high voltage circuit with a very low voltage circuit. That is called magnetic relay. Okay, high voltage circuit means what? Think about our AC, our room AC. Our room AC is going to function with 220 volts. Isn't it a high voltage circuit? I can switch it on and off by using a very small 5-volt magnetic relay. 5-volt magnetic relay will be functioning with the DC. With that, I can operate my 220-volt AC circuit. How? I'll show you in grade 10 electronics chapter. But right now we know that how these electromagnets are used in case of this magnetic relay. Because if you go to the next page, I have given you the diagram, but before that, let me discuss other uses of this electromagnet. Electric bell, the doorbell that we have. All of us, you have a doorbell at home. It contains an electromagnet which switches on and off very rapidly. The moment you place your thumb on the top of it, it starts ringing because when you're placing your hand, you're applying electricity to it, it becomes a magnet and starts ringing. And the moment you take it off, it will lose its magnetism and it will stop ringing. That is the mechanism. We have a diagram, I'll show you afterwards. And one more thing we have here, 2 more things we have here. Circuit breaker, an automatic switch which cuts off the current in a circuit if it rises above the specified value. If you remember in current electricity chapter, we discussed about this particular point that a circuit breaker actually has an electromagnet inside it which cuts off the circuit whenever a huge amount of electricity tries to come inside your flat or inside your institution due to some fault in the main circuit. Means in the main supply there can be some fault. It happens, strip down or something can happen. But for that, to stop the electricity to come to a building, we need a circuit breaker. So that is the function. And another point we have, that is a telephone. This is not the mobile that we're discussing about. This is the original old telephone, the one we used to dial. And I hope most of you never saw that telephone, right, girl? Did anybody saw that telephone? The one we used to hold the handset, put it in our ear and listen.
Yes, miss.
You saw that?
Yes.
Okay, because it became extinct now, right? Yeah. So there in the earpiece, the part we used to put in our ear to listen, there we have an electromagnet. And that electromagnet used to convert the electrical signal into the sound signal, and there's a mechanism. Of course, I'll not be able to teach you that, but you just remember in that earpiece, we have an electromagnet that helps the whole system to function. Okay, now I want to go for the next diagram, but before that, I will just take your attendance, guys. After that, I will go for the screen sharing of that diagram because without the diagram, I won't be able to explain. Okay, I want to call out the names, girls. Could you please say if you're present? Afifa, present, right?
Present, Miss.
Yes. Afnan Laiba, are you there? Afnan Laiba, I think she's
Yes.
not. You're there?
No. It's
That is,
Afnan Tulka.
yes. Afnan Kadir, I can see. Anur, are you there? Yeah, she's here. Anuj, I saw. Asya, I haven't seen her today. Guys, tell me one thing. Asya was not in my class, I think, not for even a single day. Is she joining the other day, other subjects?
No, miss.
Oh. I'm not sure what's happening to her. Asil, are you there, dear?
Yes, miss.
Fine. Now, even Fatima Tuzur, I can see. Ibtisam, today, are you in my class?
Yes, miss.
Yeah, I can see her. Ikra, are you there? I think. Is there anyone saw Ikra? Let me check. Is she there? No, I can't see her. Ikra, yeah. Ikra is joining now. Or I don't know. Is she there before? I don't know. Okay, fine. Now, Kazi Water, I can see. Marwa Zaman is not there. Reem is not here today. I think. I haven't seen her. No, Reem is not here. Reem, are you there? No. Okay. Mukarrama?
Yes, miss.
Muntaha? Nafisa? Nashita? Nimra, are you there? Nimra?
Miss.
Yes, miss.
Yes, fine. I see you. Noshin has seen. Rahma, I have seen you. Sadia Hassan. Sadia Irfan is not there, right, girls? I can't see Sadia Irfan. Sumaya Mahbub. She's here, right? Sumaya, are you there? Listen, girls, for your class evaluation, your attendance is also needed. Sumaya Mahbub, are you there? I think this girl is sleeping till now. Sajda Noor, I think she's here.
Yes, I'm here.
Sarah Islam.
Yes.
Sarah, are you here? No, she's not there. Shahad, I can't see. Luzain, are you there? Yeah, I can see her. She's
Yes,
here.
miss.
Habiba is here. Nuri, I have seen. Tasbiyan. Yanfa is not.
Yes, miss.
Yeah. Yanfa, she's not here, right, girls? Welcome back, girls. Okay, I'm waiting for the girls to join quickly. I think I'm done with my attendance. Now I will go for screen sharing one more time. And then we can go for this magnetic relay, the one I said. Quickly, girls. Yes, I'm still waiting. Only 13 students are here. Okay. So by the time you can ask me, girls, something, if you have any doubt in any topic of this thing that we have discussed till now. Do you have any doubt, girls? I think you don't have any doubt, right? Okay. So I was in the magnetic relay. As I told you, this is acting like a switch. And this switch can operate a high voltage circuit with a very low voltage circuit. And what do we mean by that? As I told you, I'm going to explain to you with a diagram that will be very clear for you. Okay, now I want to, I'm just waiting for 2 more students, I think. Okay, now let's go for the,
Miss,
yes, dear.
your voice, I'm sorry, but your voice, I can't hear it properly.
Okay, I'll be a bit loud, no problem. Okay, fine. Now, girls, as I say that we will be doing now the electromagnetic relay. Okay. Now let's go for that screen sharing one more time. I need the diagram. Yes. Now, all of you, I hope you can see that. I will go to the next page. That is all. Okay. Okay, I think now I got it. Girls, could you see the image of the magnetic relay? Let me see if they are moving. Yes, girls are moving. Let me allow them. I think they are going. Now, if you just look at the diagram, all of you girls, this is the diagram of the magnetic relay. And you know, in paper 2, you will get this diagram. They will ask you regarding the different parts and how does the function and how do they function in particular places. Okay, if you just look at it, first, if you check, it has two parts of the circuit. Means in one part, means the left side we have, that is just a single or simple electromagnet. Means we are having a source of electricity, that is a DC, which is connected to a source, and from there it has gone into a coil, you can say. And inside the coil, we place a soft iron core. And we know that soft iron is a good material which can be turned into a magnet very quickly, and it can be lose its magnetism very fast. That is why we are using it as an electromagnet. So I wrote it electromagnet. And this part is going to be known as the input circuit. Means you are going to give something to it. Or this is the one through it, you will be giving something. Okay. What you will be giving? Nothing but a signal. And if you just look at the other side, the right hand side, there I have given a contact. Look at that, a contact which is open. And on the top, there's a power supply. Even though I did not put a wave in the middle, but we can understand it is nothing but an AC circuit. And that is
a contact again.
I will tell you, these are the contacts, means it will be open when it is not functioning. And these contacts are like 2 points. You can consider this one as a key as well, a switch. There will be something, then they two will come together and the circuit will be on. Okay, we call it a contact. This contact will be open when the circuit is not functioning. Means when my switch S in the input circuit is off, then these two will be open. We call it normally open contact. And it's a very important point. That's why we have name for it as well. That it has gone to a power supply. From the power supply, it will be a motor. Now, you know the electric motor has certain functions. Basically, just discuss a simple motor that we have each and every building is having. There is nothing but motor used to lift the water from ground floor to the top floor to the reservoir. So that is the electric motor you consider. And of course, this electric motor needs 20 volt to function, isn't it? So it is a high voltage circuit. But if you just look at the whole circuit in the middle, I have written like an arrow thing, and I wrote on the iron armature, ARMATURE. Armature. This is what came from arm. Arm means hand, and this is going to actually connect these two circuits together. So if you just look at the diagram, there is a gap between these two circuits, input circuit, output circuit. But in the middle, there is an iron armature. And I told you read. Now, those who are interested in sports, you might have heard about that in the relay race. It is not school sports before we start this relay race. It means that there will be 4 students or 3 students a team. The first student will keep on running, will stick in his one hand, and she has to pass it to the second one. And after taking the stick, she has to, the second girl has to keep on running. Like that, a whole team will keep on going to complete the race, and whoever is going to do first, that will be the one. Or who's going to complete the race in a short time, will be the first one. So what is that relay? That stick you have in your hand. You have to pass the stick to your player. Then she can start running. So here also, that relay stick is acting like a iron armature is acting like a relay stick. This relay stick has to be in touch with the electromagnet, then the second circuit will be on. This output circuit will be on. But how will it get to close or how get closer to the electromagnet? We have a resistor behind it, or we have a shield behind it. So then you understand it. We have this particular diagram. This diagram is very important for us.
Miss, would you mind if you explain again?
Okay. First, as I told you, we have two circuits here. Input circuit, output circuit. And they were connected with the iron armature. This iron armature is acting like a, as I told you, a relay stick in between these two circuits. They are going to be in contact with each other whenever there is a certain time. And what we have, if you just look at the input circuit, we have an electromagnet, that is the core, and that is inside a coil. The coil is connected to a switch and a source of electricity. And this is nothing but a DC. And we know that a DC can be like around, it can be 5 volt or 4 volt, 4.5 volts, something like that. Not more than that. And then if you look at the output circuit, there we have a contact. Right now, the way the diagram is, it is open. You remember this contact has to come closer to each other. They will be in touch with each other. Then this electric motor will be switched off. Okay. Then another side, it is functioning with the power supply. And as I told you, that an electric motor needs minimum 220 volt to function with its full efficiency. So you can understand this power supply is an AC. So if you reach 1 voltage circuit, we are switching on a high voltage circuit. And how we just check what I'm saying now. Actually, I'm going to switch on the input circuit. That is, I'm going to switch on the switch S. When I'm going to switch on the switch S, the input circuit will start functioning. Isn't it? And we know that. Okay, now we can go back. Let me see what can I see there. Okay. What is concentric? Okay, Nashita, concentric means that there has to be a point. And I said the point is actually the point where the electric wire is going through. That point is the center. From that center, all the circles will be around it. So we call it concentric. They all have a common point. Okay. Okay, the last point you said, right? Okay, I'll go for that. But let me just go back to that one more time. So in magnetic relay, I was telling you that now as I switched on the switch S, means now electricity is passing to the input circuit. And when it is passing, then definitely within a few seconds, the core, which is made up of pure iron, will turn into a magnet. When it is turning into a magnet, that time it will be attracting the iron armature. Isn't it, girls? Because we know iron is a good magnetic material. So that iron armature will be getting attracted to the electromagnet. And if you just look at the arrangement, when it will come down, it will push the contact C to come closer, and if they are in touch with each other, then this circuit will be on. So what we did, we switched on the input circuit that made the core as an electromagnet and attracted the iron armature, and iron armature pushed the contact to come closer and switch on the output circuit. Did you understand the mechanism, girls? Any doubt, girls? Shall I explain more, or it's okay for you?
Yes, how will the iron armature be pushed again? I'm sorry.
Okay. As I say, the moment you're going to switch on the input circuit, it will turn into, means the core will turn into an electromagnet. So it will attract the iron armature to come down to it. Definitely, because it will be a strong magnet. Look at the terms. Of course, I didn't draw all the terms. It is a very strong electromagnet. So when it is going to attract the iron armature towards it, so if you just look at the arrangement, if it comes down, it will actually give a push to the contact because it needs a space to come down to the electromagnet. So when it is giving the push, then the two contacts will come closer and this part of the circuit will be on. Means your electric motor is going to function. And by the help of this small switch, which is acting with 5-volt circuit. Now, there's a question coming in our exam paper that, you know, that AC, as I gave you the example, since electric motor we don't use at home, if I want to switch on the AC, I can just have a switch like this beside it, the way we are using. But the thing is that every appliance needs a certain voltage to act with their fullest efficiency. So, if I connect a normal switch and the AC together in the main circuit. So the normal switch needs 5 volt minimum, consider 5 volt to function. So if it is taken 5 volt, what is left for the AC then? 215 volt, isn't it, girls? So this 215 volt might not be enough for the AC to go with its fullest efficiency. That is why we should have a relay switch which can provide particular appliances to get their required voltage. Did you understand my point, girls? Because there will be a question that why do we need to use a magnetic relay switch rather than just having any other electrical switch? Did you understand, girls? And you know that.
Ma'am.
I'll tell you again. Switch and an appliance should be connected in series, right, girls? Do you remember the circuits that we discussed? Yes. So these two will be acting like a potential divider circuit. So whatever voltage means 220 volt from the main circuit is given to us, it has to be divided into the switch and the appliance. Now let me consider an AC and the switch. So a small switch needs minimum 5 volt to function. So from 220 volt, 5 volt is taken by the switch, and 215 volt will be for the AC. So 215 volt might not be enough for the AC to show its 100% efficiency. That is why if I use a magnetic relay switch, that will ensure that my AC is getting 220 volt from the main supply. Am I right, girls? So what is this magnetic relay doing? It is ensuring that, or it ensures that every appliance is getting its required voltage to function. Clear?
Yes, ma'am.
Fine, very good. Now I don't
Wait, how does it work? How do they do that?
Did you check the diagram here, Afnan? As I said, it is going to be connected with a small switch, which is connected to a source DC, which is nothing but just a 5 volt or 2 or 3 cells will be put into that. And then in the middle, we have that iron armature, which is going to act. So for this electromagnet or electromagnetic relay, we'll have a separate connection. With that connection, we can use this one. You'll just wait, you'll see it in electronics chapter, we'll be having the function of this. That time we'll discuss. But right now, you'll remember it is a switch which actually allows to switch on a high voltage circuit with a low voltage circuit. Okay? Now, all of you, do I need to read out the whole thing first? Okay, let me just read one time. Okay, I wrote it over here that when the switch S in the input circuit is closed, means the circuit is on, a current flows through the solenoid and the core becomes an electromagnet. It pulls the soft iron armature towards it, which closes the contact C. Because the arrangement will be done in a way that when it is coming closer or it is pulled by the electromagnet, it will give a push to the contact so that the two contacts can come close together and switch on the output circuit. Okay, so we wrote, as a result, a current flows to the motor and the output circuit is on. The above relay is of normally open type. Now, let me remind you, we have to discuss these 2 points because if you just look at the diagram that I gave you for the magnetic relay, you notice 2 things here, contact C and the switch S. Switch S is open, means it is off, as well as contact C is also off. But contact C is important because when the input circuit is off, this is also off. We call it normally open relay. Means in normal case, when electricity is not passing through the circuit, it will be, the contact C will be open. So we call it normally open relay. We have another one which is called normally closed relay. I'll come to that later. But first you check, I wrote it here. The above relay is of normally open type. When the input switch is off, output switch is also off. Both of them are off. Now, in normally closed relay, the input switch is off, but the output switch is on. So there's a difference. Input off, output on. How? I will give you the diagram afterwards. It's there. Now, I have given you the 2 symbols. How do we symbolize them? First one, if you check, the coil I have shown you, and then the switch is open. And the second one, the coil is there, but the switch is closed. So we wrote it switch closed. Normally open relay, normally closed relay. We have 2 types, and for the 2 types, we have 2 different diagrams. Okay. Now I just want to go back to the screen sharing one more time because I need to discuss the next diagram with this. I hope you can see my screen, and I am giving you the diagram one more time. Yes. Now we are in the diagram of the electric bell, the one I was telling you that in our doorbell, we have a mechanism that allows, after passing the electricity, the core will turn into a magnet and a procedure will be there that allows the bell to ring. If you just look at it, I didn't give you the source as alternating current, but you can just consider alternating current in the same. If you just look at the first part, here, this is the switch that is beside the source. That is the one you actually press, the switch. We wrote output switch on, input switch off. Okay, let me see here. Did I make any mistake? Output switch off. Yes, output means this is the hammer and the gong. Did you notice here? Output switch on. Okay, beside it, did you notice 2 small boxes that I have here, girls? Did you notice 2 small boxes here? Just beside the hammer. That is the output switch. And isn't it on? Isn't it closer together? They're in touch with each other. Can I see that?
Yes.
Yes, so they are on. But you can output switch, sorry, input switch beside the cell, it is off. Means it is right now, the bell is not functioning. So think about it, going home, and now you're going to press it. So you press that, our input switch. So the input switch is on, and with the situation, what happens to the output switch? It came out apart from each other. Why? Because when you switch on the input switch, that electricity will pass at this coil, will become a magnet. Means the coil inside the coil, where we have our core, that core will become a magnet. And when it is becoming a magnet, what itself will become a magnet and will attract the hammer. So the hammer is coming to the ground and will start beating, or start beating, and we will hear the sound. Look at that connection, the one which was on, it became off now. Right, guys? Because it closes the bomb and it started doing there. As long as you switch it on, means you're turning on the top of the switch, input switch, it will become a magnet and we want it to be on. And then that will be off. So we say that output switch becomes off, input switch on, bell starts to ring. is that it uses normally closed relay. So if you look at the first diagram, normally beside the hammer, the two contact, the one we are seeing C, contact C.
Is the magnetic relay uses open type or closed relay?
Magnetic relay is open, normally open. In electric bell, normally closed. Okay, that is the difference because it has two different functions. Okay, I think we are done with it, but next week I will be continuing from here. But I think this week, whenever I'm getting time, I'll send you more pages or more parts of the note so that you can write down and then we can have a discussion. So now tell me, guys.
Fifth point.
Oh, that fifth one. Okay. I told you that whenever we are having a wire passing to a card or a paper, just consider your paper, the papers we used to write. We'll make a hole and then pass the wire through it and give a connection to it. Okay, we got a circular, as I said, you're going to sprinkle some iron fillings and it will create a magnetic field. So how to know what will be the direction of the magnetic field? As I said, we can go with the right and left route, or we can do one more thing, that is, we can just place a north pole there. A single north pole. As I told you, that is impossible kind of getting a low north pole. But if I place a north pole, the north pole will experience a force from that particular magnetic field. And that can give us the direction of that. Okay, so you just remember this much because in 11 we'll discuss more about it with the diagrams and all. Okay, fine. So inshallah, today we are going to finish our class. We have completed till that magnetic relay. I want you to go through it during the weekend, and if you have any query, you can message me anytime. I will try to solve it. And inshallah, next week, as I said, it will be the Ramadan time. Then I'll be having a class with you, like it will be from 10 to 11. In the morning, 10 to 11, I'll be having 2 classes with you, both the days, Wednesday and Thursday. Inshallah, I'll meet you again next week. Okay, girls? Yes, all of you, pray for us. Allah Hafiz, girls.
Bye.
Bye.
Bye for now.